Hello everyone! We had already learned about the concept of sets, the basic relationships between sets, and the basic operations of sets. Today, we will learn together about reading and thinking the number of elements in a set. Let's first take a look at the practical problem in example 1. A certain supermarket purchased goods twice. The first purchase included ballpoint pens, fountain pens, erasers, notebooks, instant noodles, and soda water, totaling 6 types of products. The second batch of goods includes ballpoint pens, pencils, ham sausages, and instant noodles, totaling 4 types of products. May I ask how many goods were imported into this supermarket twice in total? What mathematical object should we use to study the above problem? We can consider this problem from the perspective of sets. If set A represents the variety of the first purchase and set B represents the variety of the second purchase, then the elements in set A and set B can be listed one by one using the enumeration method. Set A consists of ballpoint pens, fountain pens, erasers, notebooks, instant noodles, and soda, while set B consists of ballpoint pens, pencils, sausages, and instant noodles. The set consisting of 2 types of purchases is the union A and B of sets A and B. Find the total number of goods received twice, that is the number of elements in set A and B. So what is the exact number of elements in A and B? To answer this question, we first need to understand the definition of the finite set cardinality card A. A set can be divided into finite and infinite sets based on whether the number of elements is countable or not. We call a set containing a finite number of elements a finite set, and a set containing an infinite number of elements an infinite set. Card A is used to represent the number of elements in a finite set, also known as the cardinality, and we specify that the cardinality of an empty set is 0. After clarifying the definition of cardinality, let's find the cardinality of the following sets together. For problem 1, there are 5 elements in set A, 0, 1, 2, 3, 4, where card A equals 5. It represents that the number of elements in set A is 5. For problem 2, if the elements in set A satisfy that x is greater than 1 and less than 3, and x belongs to a natural number, then there are only 1 elements in set A. Card A is equal to 1. For problem 3, if set A is all prime numbers and elements in set B satisfy x greater than 3 and less than 15, then the elements of set A intersecting with B are 5, 7, 11, and 13. Its cardinality is 4. For question 4, if the elements in set A are 1, 2, 3, 4, and the elements in set B are 1, 2, it is obvious that the elements of A and B are 1, 2, 3, 4. Its cardinality is 4, but in reality, A and B are the set. Why is this? Because set B is a subset of set A, the number of elements in set A and B is equal to the number of elements in set A. If the elements in set A are 1, 2, 3, or 4, and the elements in set B become 5, 6, or 7, the intersection of sets A and B at this time is an empty set, and the number of union elements is the sum of their respective element numbers. Its cardinality is 7 if the elements in set A are 1, 2, 3, 4. The elements in set B are 3, 4, 5, and 6. The cardinality of a union is 6. At this point, A intersecting B is not an empty set, and the number of union elements is the sum of their respective element numbers minus the number of repeated elements. Through question 4, we can find that for 2 sets A and B that have an intersection, the cardinality of their union is not simply the sum of A's cardinality and B's cardinality, but the addition requires subtracting the number of common elements in the 2 sets. Next, let's answer question 5. How many types of goods were imported in question 1? We can use the enumeration method to list sets A and B without repetition or omission. This process should pay attention to the heterogeneity of elements. Count out that there are 8 elements in set A and B, that is, card A and B are equal to 8. A total of 8 types of goods were received in 2 days. Question 6 is the total number of goods received in 2 days directly added up by 6 and 4. This statement is obviously incorrect. In this issue, there are 2 shipments of the same variety, namely ballpoint pens and instant noodles. For 2 sets with intersection, if the cardinality of their union is directly added by their respective cardinality, it will double calculate the same variety of goods that are entered twice, and the repeated cardinality needs to be subtracted. Repetitive varieties can be represented by a crossing B. The elements corresponding to A and B are ballpoint pens and instant noodles. We can calculate that card A is equal to 6. Card B is equal to 4. Card A and B are equal to 2. The base of the actual purchase variety set A and B is 8, which means that card A and B are equal to card A plus card B minus card A and B equals 8. Actually, 8 types of goods were imported. Can we generalize the equation we have derived to a more general case? We can use Venn diagrams to study. In the Venn diagram below, 2 ellipses are divided into 3 regions, and the number of elements in each region is denoted as 1, 2, and 3, respectively. So the areas corresponding to card A are 1 and 2, and the areas corresponding to card B are 2 and 3. Card A intersects with B in the middle area. The correctness of the equation is demonstrated by the fact that the area corresponding to the intersection of card A and B is the same by adding card A and subtracting card B from card A, since both sets A and B can be arbitrarily selected in this process. The equation holds for all finite orders A and B. So we have elevated it to a mathematical formula. Generally, for 2 finite sets A and B, we can write an identity such that card A and B are equal to card A plus card B minus card A intersecting B. Since when A intersects B with an empty set, the cardinality of the empty set is 0, this identity can be applied to any set A and B. We call this property the principle of inclusion and exclusion of 2 sets. We have extended the mathematical formula we obtained from example 1 to the general principle of inclusion and exclusion, going through a process from special to general. Next, we will apply the principle of inclusion-exclusion to answer relevant practical questions. Example 2, the school first held a track and field sports meeting, and 8 students from a certain class participated. Another ball sports meet was held, with 12 students from this class participating. 3 students participated in both games. How many students from this class participated in the 2 sports events? We also use the language of sets to express ourselves and use the principle of inclusion and exclusion to solve this problem. Use set A to represent students participating in track and field events, and set B to represent students participating in ball games. So set A to B are the students who participated in both sports events, and set A and B are the students who participated. Based on the relationship in the question, we have obtained the above data. By substituting it into the inclusion-exclusion principle formula, we can obtain card A and B equal to 17. So, a total of 17 students from this class participated in the 2 sports events. We can also use Venn diagrams to solve this problem. Since the intersection of card A and B equals 3, fill in the area where A intersects B in the diagram with 3 first. Note that 3 here represents the number of elements, not the number of elements in the set. We have added parentheses in the picture, and the same applies to the other 2 places. And card A is equal to 8, so we subtract 3 from 8 to get the remaining number of elements in set as 5. Similarly, card B equals 12, and subtracting 3 from 12 gives the remaining number of elements in set B 9. Finally, add the number of elements in the 3 parts A, B, and A intersecting with B, and the value of card A and B is 17. Next, we will proceed with the variation of example 1. A certain supermarket purchased goods 3 times. The first time they purchased 30 types of goods, the second time they purchased 20 types of goods, and the third time they purchased 20 types of goods. There were 10 types of goods imported in the first 2 times, 8 types of goods imported in the last 2 times, 15 types of goods imported in the first and third times, and 6 types of goods imported in the third time. Q. How many types of goods have been imported in total? We can use sets A, B, and C to represent the varieties of these 3 purchases. So set A to B represents the varieties that were purchased both the first and second time. Similarly, set B intersects with set C and set A intersects with set C can be represented using descriptive methods. The above data is obtained from the relationship between the questions. Request the total number of varieties for 3 purchases, that is card A, B, and C. We can still use Venn diagrams to study this problem. The intersection of A, B, and C equals 6. We first fill in the number 6 at the intersection of A, B, and C card A crossing B is equal to 10. Subtracting 6 from 10 gives that the remaining number of elements in a crossing B is 4. Similarly, based on card B crossing C being equal to 8 and card A crossing C being equal to 15, we obtain that the number of remaining elements in B crossing C is 2, and the number of remaining elements in a crossing C is 9. Since card A is equal to 30, we subtract 6, 4, and 9 from 30 to obtain 11 for the remaining elements of set A. Similarly, we can conclude that the remaining elements of B and C are 8 and 3, respectively. As shown in the figure, we add the number of elements in each block to obtain the value of card A and B and C, which is 6 plus 4 plus 2 plus 9 plus 11 plus 8 plus 3, equal to 43. It can also be seen as adding the number of elements in sets A, B, and C, subtracting the common parts of the three sets, and adding the common parts of the three sets, that is, 30 plus 20 minus 10 minus 8 minus 15 plus 6 equals 43. Therefore, we consider the formula for the number of elements in the union of three finite sets. Please divide into groups and discuss it using a Venn diagram. Yes, the analysis process of the variant in example 1 is similar to the reasoning method of calculating the number of elements into sets combined. We can get it! For three finite sets A, B, and C, card A and B and C is equal to card A plus card B plus card C, minus card A intersects B, minus card A intersects C, minus card B intersects C, and adding card A intersects B intersects C. This mathematical property is called the inclusion-exclusion principle of three sets. We note that this identity adds the cardinality of the intersection of three sets after subtracting the cardinality of the intersection of two sets. This is because in the process of subtracting the cardinality of the intersection of two sets, we subtract the part of the intersection of three sets twice, so it needs to be added back. This principle can be proven using the inclusion-exclusion principle of two sets. Students who are interested can try the process of deriving the proof after class. Using this conclusion, we will solve the following practical problem. There are a total of 249 high school seniors in a certain school, and the number and subjects with excellent final exam results are shown in the table below. Some people say that the statistical table above is incorrect. What do you think? According to the inclusion-exclusion principle formula derived from the data in the statistical table and applied to three sets, it can be concluded that there are a total of 251 students in the third year of high school, which contradicts the actual 249 students. Therefore, there is an error in the statistical table. We have just learned how to calculate the number of elements in a union of two sets and a union of three sets. We can count the number of elements in a finite set one by one for comparison. For a set with an infinite number of elements, such as set A being 1, 2, 3, 4, n, etc., and set B being 2, 4, 6, 8, to n, etc., what is the relationship between sets A and B? Can you design a method to compare the number of elements in these two sets? Yes, set B can be seen as a subset of A. So must the elements in set B be fewer than those in set A. If it is a finite set and B is a true subset of A, then the answer is affirmative, as B must have fewer elements than A. However, from the perspective of an infinite set, to compare the number of elements between A and B, it is necessary to find the relationship between A and B. We can establish a one-to-one correspondence between A and B by multiplying by 2. That is to say, given an element in A, there must be an element corresponding to it in B. Element 1 in A corresponds to element 2 in B, and element 4 in A corresponds to element 8 in B. From this perspective, A and B have the same number of elements. Therefore, for an infinite set, we need to compare the number of its elements. As long as a one-to-one correspondence is established between two sets, we determine that the number of elements in these two sets is equal. There has been a qualitative change from finite to infinite. The number of elements in A is infinite, and the number of elements in B is also infinite. We cannot count the number of elements in a set, which does not affect the equality of the number of elements between them. So, can you answer the fourth question now? Are there as many elements in sets n and n stars as each other? The elements in n are 0, 1, 2, 3, n, etc. N stars range from magnitude 1 to n. We can consider each element of n star as adding 1 to each element in n. If the elements in N are denoted as X and the elements in N star are denoted as Y, then a one-to-one correspondence is established between these two sets, so they have the same number of elements. In summary, the key to comparing the size relationship of an infinite set of elements is whether a one-to-one correspondence can be established. Of course, this issue can be further studied in depth and will not be expanded here. Interested students can search for relevant materials for learning after class. Finally, please think about what we have learned in this class. Let's review together. A symbol, also known as the cardinality, represents the number of elements in a finite set A, denoted as card A, a formula that calculates the elements of the union of two finite sets and extends it to the form of three sets. In this process, we went through the transition from natural language, symbolic language to graphic language. Finally, we explored together a fundamental principle of equal number of elements into infinite sets.